Okay, so the main topic that we're gonna spend some time studying is this thing called linear equations. Okay. In general, they look like this. You take this form. So a1 x1 plus a2 x2 plus an xn equals to b, where a1, a2, an, and b, these are numbers, and x1, x2, xn, these are unknowns, or as we usually call it, variables. Okay. Now, for example, we could have x1 plus 2x2 plus x3 equals to 1. That's a linear equation. You could also have 3x1 minus x2 plus x3 plus 4x4 equals to 5, for example. Now, there are anything that's not of this form is not a linear equation. Okay, so for non-examples, for example, let's say you have x squared plus x plus 1 equal to 0. This is not an example. Let's say you have an x plus sine x equals to 0. That's not an example. You have x1 plus x2 e to the x3 equals to 4. That's not an example. I mean, there are many non-examples as there are many examples. So, I mean, you just have to keep in mind that for linear equations, you really want them to look like this. Okay, so then these are kind of things that we want to study. Now, not only that, we want to study this thing called linear systems. And these are just a collection. They're just a collection or as we call it, system of linear equations. So instead of having just one, you may have, well, you have more than one. So for example, say, say you could have x1 plus x2 equals 3, x1 minus x2 equals to 1. These two put together is a system of linear equations. Now, and we can come up with many more examples. They don't have to have just two equations. You could have, for example, and there are three variables, say x1 plus x2 plus x3 equals 4. x1 minus x2 plus x3 equals 5. And maybe you have one more equation, x1 plus 2x2 plus 3x3 equals to 6. And similarly. Okay. So now, in general, you could have, I mean, we consider things like m by n system of linear equations. This just means, well, these are the following things. So m by n system of linear equations are of the following form. A11x1, A12x2 plus plus A1n xn equals, say, B1. Now A21 x1 plus A22 x2 plus A2n xn goes to B2, and likewise continuing on to a m1 x1 plus a m2 x2 plus a mn xn goes to bn. So first of all, this is what we call a system, m by n system of linear equations. And just like for linear equations, there's a11, a12 to a1n, a21, a22, a2n, all the way down to am1, am2, amn. These are numbers. Now x1, x2, xn, these are variables or unknowns. Okay, so in general, that's what we call the m by n. So we call m by n system of linear equations. Okay, for example, and we're going to be spending most of our focus on 3x3 examples, or namely 3x3 system, and they take this form. Take a11 x1, a12 x2, a13 x3 equals b1, a21 x21, a22 x2, a23 x3 goes to b2, a31 x1 plus a32 x2 plus a33 x3 equals to b3. Now, going back to the general form, I mean, there's something to say about the way these indices are made. So, see the first index here, 1, 2, and m, and all down to m. These are indices indicating in which equation these numbers are. Okay, so the 1 here means it's in the first equation. Likewise here, the 2 here means it's in the second equation. The m here means it's in the mth equation. Now, the second index indicates, in the particular equation which variable it's attached to. So this second one here indicates is the variable is attached to x1. This indicates it's attached to x2, and similarly here, and likewise here and there. Okay. So now we're interested in systems of linear equations because they often appear in practice. These unknowns usually appears as some quantities that we don't know but we would like to know, and these equations happen to be constraints or properties that these unknowns are supposed to satisfy. So what we really want to know about linear systems is their solutions. Right. Now, so a solution to a linear system, say m by n linear system of linear equations is just a sequence of numbers. Sequence of numbers. Say S1, S2, Sn, such that remember the m by n system of linear equation is here. Okay. Now, such that if set if we these numbers for these numbers S1 through Sn to be a solution to the m by n system, we need that if we set x1, the unknown x1 to be equal to S1, x2 equals to S2, and so on. And finally, xn equals to Sn, then all equations in the system whole. Okay. So for example, if I have this system, 2x1 minus x2 minus 3x3 equals to minus 1 minus x, I don't want this, minus 2x1 plus 2x2 plus 5x3 equals to 3. Okay, let's say we have this system of linear two equations in three unknowns. So this is a 2 by 3 system. Okay. Now a solution that would, for example, be x1 equals to 1 x2 equals to 0, x3 equals to 1. And we can check that this indeed is a solution, because check. So 2 times, I want x1 to be 1, x1 to be 1, x2 to be 0, and x3 to be 1. So I substitute these into the equations. The first equation I'm looking at 2 times 1 minus 0 minus 3 times 1. That's 2 minus 3, which is minus 1. The second equation I'm looking at minus 2 times 1 plus 2 times 0 plus 5 times 1. That's minus 2 plus 5, that's 3. Okay, that's indeed the case. Now in some cases, namely for for cases with 2 or 3 variables, we can interpret linear equations geometrically, as you may have seen in calculus or analytic geometry. Interpret linear equations geometrically. Now, let's say 2 variable case. In 2 variable case, let's say I have, that's a11x1 plus a12x2 equals to b1, and a21x1 plus a22x2 equals to b2. Now, the point is that each equation when you think of each equation corresponds to a straight line on the plane. Right, when you think of x1, the pair x1, x2 as a point on the plane, then point satisfying this linear equation on the plane gives you a straight line on the plane. Now, so when there are 2 equations, so when there are 2 equations, like what it is here, there are the following possibilities. Okay. Like I said, each linear equation gives you a straight line on the plane. So therefore we have 2 equations, meaning 2 lines. So we have, let's first of all draw the x1, x2 axes, and I have 2 equations, 2 lines. right? So first, typically they look like these. You have two lines, right? One line for each equation. And now there's this point here. This point on both lines, this point being on both lines means that it corresponds, it corresponds to a solution. It corresponds to a pair of numbers making both equations true. So that therefore corresponds to a solution to the system, right? And the fact that you see only one such point means that in this situation, the system has a unique solution. Okay, now okay. Now the next possibility is next possibility. Okay, so sorry, this is should be x1, x2, and you have two lines. They may not meet each other. Sorry, these lines are not very straight. But anyway, my point being that there's no intersections. No intersections of no points of intersections. Now, as we've said already, these lines, each line is the set of, each line corresponds to an equation. Points on the lines correspond to solutions to the equations. So, but these two lines don't intersect, and that means that there is no solutions, for both equations at the same time. So this is a situation where the system has no solution. Okay. Let's see. So the last possibility is this: x1, x2. Right. Again, each equation corresponds to one line. Oops. Now, it may just happen that both equations give you the same line. Okay, so I should write this down somehow. So two lines are the same. Two lines are identical. Two lines are the same. Now again, points on the lines, points on each line correspond to solutions to each linear equation. Now, both equations give you the same line. So any point on this line is a solution to both equations. So in this case, what we have is you have infinitely many solutions to the system. Okay, so these are the three possibilities. Now, in the three variable case, sorry, you can discuss the situation similarly in three variable case. Okay, so we would have, let's say, three equations, a11 x1 plus a12 x2 plus a13 x3 equals b1, a21 x1 plus a22 x2 plus a23 x3 equals to b2, a31 x1 plus a32 x2 plus a33 x3 equals to b3. Okay. Now, so what's the geometry here? So in three variable case, a linear equation correspond, again, what I should do is remind you that triple x1, x2, x3 here correspond to a point in space, three-dimensional space. Now, a linear equation correspond to a plane in space. So we have, say, three equations that correspond to three planes. Now, three equations correspond to three planes. Solution, and just like the two variable case, solutions to the system correspond, correspond to common intersections of these planes, right? Because points on the plane are solutions to the equations, corresponding equation. If you want a solution to all three equations, the corresponding point has to be on all three planes. So it must be common intersection. Okay. So now there are several possibilities. Okay, for example, you could have, now this is difficult to draw. You could have three planes all parallel to each other, right? They don't meet at all. And in this case, there's no solution because solutions must be common intersection points, and there is no common intersection points here. Now, another possibility would be, okay, you have two planes that intersect. Okay, and And maybe the third plane also passes through these axes of line of intersection. So that will be maybe something like these. And there is a common line of intersections here. Okay, and this is a line, so it's got infinitely many points. Therefore, you have infinitely many solutions. Okay. Now, well, there are other possibilities, of course. You could have, how do I draw this? Could have two parallel planes and being intersect by a third one. Okay, so so let's see. So these two planes, so this top plane and the vertical plane here, they intersect along this line. And this bottom plane and these vertical plane, they intersect along this red line. But these two lines don't intersect. So as far as common intersection points for the three planes is concerned, there's no solution. Okay. Now, there are other possibilities, of course. You could have, say, a plane like these, a plane like that, and a third plane. Let's first draw. Let's first draw the line of intersection of these two planes. They intersect along such a line. And there's a third plane. Intersecting like that. And the third plane and the horizontal plane intersect along a red line like these. And there is a common intersection point. And there's only one common intersection point, so this is the case of a unique solution, etc. Okay. So, I mean, what this is meant to say is that, okay, you could, in some cases, in two variable or three variable cases where you have clearly visible geometric interpretations of linear equations, you can think of solutions to linear equations as common intersection points, as I say here, of these geometric objects. Okay. All right, now there's a definition to make. I mean, we are interested in solutions to linear equations. is related, that this definition is related to that. A linear system is called consistent if it has at least one solution. I mean, as we've seen these examples above, I mean, they could have more than one solutions. In fact, they tend to, once there is more than one solutions, they tend to have infinitely many solutions. But the definition is just about having a solution or not. If it has a solution, it's called consistent. It's called inconsistent if there is no solution. Or if it has no solution. Okay. Sorry. Okay, so it's consistent or inconsistent. So obviously it's either one way or the other. It's either consistent or inconsistent. For example, over here in this situation where 3 planes intersecting at a unique point, this is consistent. And where in this situation it's inconsistent. Over here, you have 3 planes intersecting along a line. It's got infinitely many solutions, so it's consistent. Okay. And finally, when you have 3 parallel planes, there is no solution, so it's inconsistent. Okay. Now we introduce the important gadget for basically this course is the notion of matrices. All right. I mean, this is not something crazy. Essentially, it's a collection. It's an array of numbers. Well, for us, usually numbers. Okay. So, for example, you could have, 1, 2, 3, 4, 5, 6. Yeah, that's not a 6. 7, 9, 8. Okay, that's one example. You could have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's another example. You could have, I don't know, 7, 2, 6, 4, 9, 9, 1, 2, 1, 8, say. Okay, so now again, this, as you can see here, it's a collection of numbers arranged in some ways. So we should first of all mention some specific things about this arrangement. And let's see. So number of rows. So in this example, the number of rows is 3. It's got 3 rows. The number of columns is also 3. Now in this example, the number of rows is how many? You got 2 rows. The number of columns, you got 5. Right? Now in this last example, the number of rows is 1, 2, 3, and 4. The number of columns is 2. Okay, so in this case, in the first case, where maybe I should label them 1, 2, 3. In the first case, where the row you have 3 rows and 3 columns, it's called 3 by 3. In the second case, where you have 2 rows and 5 columns, it's called 2 by 5. 3 by 3 matrix, I'm sorry. The first case is a 3 by 3 matrix. Second case is a 2 by 5 matrix. And finally, the third example is a 4 by 2 matrix. Okay. In general, you can talk about m by m matrices. M matrices are of the form again, just like you see in these previous examples, this first number here indicates the number of rows. The second number here is the number of columns. Okay, so an m by m matrix is therefore of the following form. A11, A12, up to A1n being the first row. Right, each row here should have n numbers because you have n columns. A21, A22, A2n, and you'll have m row, AM1, AM2, AMN. Okay. Now, all right, so again, let's just keep in mind that in my notations here, each symbol here has 2 indices. The first index indicates the row in which the number or the symbol is placed, and the second index indicates the column in which the symbol is placed. Okay, so let me maybe should write that down. First index indicates row. Second index indicates column. Okay, so very well. What are we going to do with this? And why is this supposed to be sort of important for this course? Well, the first reason is this. We can use matrices to describe or to represent, hold on, linear systems. Okay, that's somehow the first reason for considering matrices. Now let's do an example first. Let's say we have this system, x1 plus 2x2, x3 equals 4, 2x1 minus x2 minus x3 equals 1, x1 plus x2 plus 3x3 equals 0, say. Okay, so now you obviously see that you've been writing x1s, x2s, and x3s, many times. The important things to remember about this system is the following: are the numbers associated to this, right? Namely, over here is a 1 in front of x1. So maybe I should do that. There's a 1 in front of x1, 1 in front of x3. There's a minus 1. There's a minus 1 here, there. There's a 1, there's a 1. And one, to describe this linear system, well, you need to know these numbers in front of the variables, and also the numbers appearing on the right hand side. First of all, maybe I should use a different color. Try again. So these things that highlight in yellow, the numbers appearing in front of the variables, these are called coefficients. Now, the numbers appearing on the right-hand side are called constants. Okay, and we can just introduce a matrix to keep track of these quantities. 1, right? Just keep these numbers, keep the coefficients and the constants in their position. 1, 2, 1, 4. 2 minus 1, minus 1, 1. 1, 1, 3, 0. Okay. And if you want to remind yourself about the difference between coefficients and constants, you could put a dashed line here. And this is a matrix, as you can see. This matrix is called the augmented matrix. For the system. Now, if you just have, without the constants, if you just have the coefficients, this is called the coefficient matrix of the system. Okay. Now you could see how things should work in general. In general, let's see, I need some space. In general, if I have an m by n n system, of linear equations, like this: a11 x1, a12 x2, a1n xn, b1, a21 x1, a22 x2, a2n xn, b2, and so on to n1, sorry, m1 x1, m2 x2, mn xn goes to bn. If you have this m by n system of linear equations, we can get, we have two matrices associated to this. And those are first of all, you have the augmented matrix. Now this is well, of the following: 1, a12, a1n, a21, a22, a2n, a m1, a m2, a mn, and like I did before, let's put a dashed line here, and I'll put the constants. Now this is of size m by m plus 1. Right? Because it has m plus 1 columns. And the other matrix we can introduce is the coefficient matrix. And it's just this augmented matrix without the last column. So a11, a12, a1n, a21, a22, a2n, am1, am2, amn. Now this one is a m by n matrix. Okay, and so that's what we want. That's what we have now. And as you can obviously see, these two matrices, well, in fact, just the augmented matrix. Augmented matrix records everything you need to know about the linear system. Okay, and so yeah, so that's all I want to talk about now. And the next lecture we'll see how to work with matrices and what that means for the corresponding linear systems. Okay.